Okay. So let's talk about glomerular filtration. So again, you've got this afferent arteriole coming in, these leaky capillaries that are the glomerulus. Again, these are fenestrated capillaries, so they got little holes, little pores. Where is the efferent arteriole heading to after the glomerulus?
Second bed of capillaries.
So this is heading off to the peritubular.
Peritubular.
Right, so this, again, and we're gonna follow that later. When we get to the reabsorption and secretion, we're gonna care about that. But for right now, we're keeping our focus on the very beginning of the process, the filtration. And again, like I said, the tubule kind of starts here, kind of, it's like a baseball mitt kind of grabbing a ball. We call this the Bowman's capsule. The cells of the Bowman's capsule actually kind of grab around the capillaries to help create this, what we call a filtration membrane. Whoops. It's actually a mix of fenestrated capillaries and then these cells, which we call podocytes. That make these little filtration slits. They're also called slit pores. So between the pores of the fenestrated capillary and these filtration slits from these little cells that are actually from the tubule itself that are kind of glomming around the capillary, that's going to create this filtration membrane, which, if it's functioning properly, is going to allow water and small solutes to go through. So again, water and small solutes. Basically 3 microns. Anything smaller than this can go through. As you get into larger, it gets a little more complicated because charge comes into it as well. But basically, we can say by the time you get to 7 to 9 microns, everything is blocked. Things to remember. So no cells, no plasma proteins. Right, so cells and plasma proteins stay in the bloodstream. If those are starting to get out there, there's a problem with this filtration membrane. And now what we want to talk about is what actually drives the filtration. And like I mentioned, it's going to be particularly that blood pressure, 55 millimeters of mercury of blood pressure pushing in here, which is causing the fluid to leak out. So we're going to look at this in a little more detail now. So we talked about 55 millimeters of mercury coming in, fluid. So we're going to talk about NFP, the net filtration pressure. Hold on, I'm getting sloppy. Let me get less sloppy. So net filtration pressure, that is what's ultimately driving the filtration. And it's going to have the main driver, like I said, is this glomerular hydrostatic pressure. Which I said is about usually 55 millimeters of mercury. What kind of things are going to fight it?
Osmotic pressure.
Absolutely. Right? As more and more water leaves and we still have those plasma proteins and stuff that are staying in the blood, there's going to be more and more of an osmotic pressure pulling back into the bloodstream. Kind of the same thing we saw in the continuous capillary beds, right? So the osmotic pressure ends up being pretty big, like around 30 millimeters of mercury. And then you also just get the back pressure. The more you're kind of shoving water into this limited space, you get kind of a back pressure building up. So we call the capsular pressure, hydrostatic pressure. This is basically kind of the back pressure. And this is somewhere around 15 millimeters of mercury. So if we look at all of these together, the NFP, the net filtration pressure, it's about 10 millimeters of mercury. So this is what is ultimately driving this. This is why your kidneys really care about keeping your blood pressure high enough, because if this is not adequate, you're not going to have your kidneys working. In fact, if your blood pressure drops too far, I have like some, what is it? Regulation. Here it is. Yeah, so I guess this makes sense. Like if your mean arterial pressure drops below 45, which is basically this here, you're in your total renal failure, right? So you have lots of ways. We're going to talk a little more. You have ways to adjust this net filtration pressure over a wide range of blood pressures. So, you can kind of So like if your blood pressure is pretty low or pretty high, we're going to talk about different ways that the system has to adjust this net filtration pressure to make sure that it's in the adequate range. But if your blood pressure gets way too high, you might be driving it too hard, Or if your blood pressure gets really low, that's going to affect the ability of your kidneys to be functioning properly because you're not going to be making adequate filtrate. So again, having low blood pressure is going to affect your kidneys. So net filtration pressure is driving what we call the glomerular filtration rate. So you should know this GFR. Right, this is like driven by the net filtration pressure. And we've just mentioned this already. This is around, usually 10% of the incoming flow. So this is going to be, 20 to 25% of that 5 liters per minute. So it's around 100 to like 125 milliliters per minute. This is a typical glomerular, and this is across all the nephrons in both kidneys. Right, so I'm going to be like drawing picture of the nephron and saying, oh, here we got like 125 mils per minute or something, but that's like if you add all the nephrons together. This is something that is, clinically people check to make sure your kidneys are functioning properly. There's a few different ways you can try to assess this glomerular filtration rate. You can look at things that are being produced in the body that are being excreted and seeing kind of how quickly they're showing up in your urine. Again, if we go back to this picture here, like if there's this kind of an amount of stuff in the blood that's becoming filtrate and then is getting going to show up in the urine. So things that are like creatinine, which is a byproduct of muscle metabolism. You can look at how much of that is showing up in the urine, and it's going to kind of give you a sense of how much filtrate is being formed per minute. If you see like how fast is it showing up in your urine. If you want to get a more accurate readout of glomerular filtration rate, there's this actually cool thing where there's this sugar called inulin. If you put inulin, it gets here, and this is not absorbed or secreted. So it won't get absorbed or secreted, which means any of the inulin that is leaving the capillaries and becoming filtrate is going to end up becoming urine, since it is not reabsorbed or secreted. So you just look at the rate that inulin is showing up in the urine that's forming, and that gives you a readout on the glomerular filtration rate. So you can actually get a measure of glomerular filtration rate by using this inulin test, which is kind of cool. So GFR, glomerular filtration rate. Now what we're going to do is shift into the bigger picture. There's the glomerulus. Here's our Bowman's capsule. Here's our filtrate that's forming. What we're going to be doing as we follow this filtrate and its journey from being filtrate to becoming urine, we're going to look at two different qualities of the filtrate. We're going to look at both how much is still there, and we're also going to be following osmolarity. Like, what's the osmolarity of the filtrate? Because that's actually going to be really interesting and useful in understanding this process. So at each stage of the game here, we're going to look. So if we look at the very beginning, how much filtrate is being formed? We just mentioned it, the glomerular filtration rate.
(125 milliliters per minute).
Exactly. In order to make the math easier for this part of the lecture, I'm going to do the 100 one. So about 100 mils per minute. If we look across all the kidneys, and like I said, this is over 150 liters per day. So obviously this is mostly going to be reabsorbed before we're done with all of the tubule. In terms of osmolarity, both water and solutes are leaving kind of in relatively equal proportion. So which means, what's the osmolarity going to be as we go here?
Be the same.
It's going to be the same, which is what? Right, 300 milliosmolar. That should sound familiar.
Of course, of course.
Right? It's the same it's the osmolarity of everything else in your body. So this is where we're going to start. And then we're going to be going into what we call the PCT, the proximal convoluted tubule. And then we're going to go down into the loop of Henley, descending limb, the ascending limb. We're going to go up into the distal convoluted tubule. Ultimately going to go into the collecting duct. We're going to be going into all these different parts. We're going to talk about all these processes. By the very end, you'll have urine, but there's going to be lots of steps in between. The nephron. All right. So we have our nephron here, this big kidney tubule. It's got all these different sections. And we have talked about this first part, the Bowman's capsule and filtration. We've talked about that in depth. And that's leading us to this kind of entrance to the renal tubule here. We've got about 100 mils per minute coming in. And I said it's about, it's isoosmotic with your normal body fluids because you're losing both solute and water during filtration. So the next big section is what we call the PCT, or proximal convoluted tubule. So the proximal convoluted tubule, this is mainly a place for reabsorption. So this is about like 65% of filters. I keep making a capital. I don't want the capital. Let's forget it. So the PCT, so obviously to make this picture make more sense, I should put the peritubular capillaries. Obviously the peritubular capillaries are all over the place here. So this is where we take in the stuff we want to keep that's still in the tubule and moving it into the bloodstream. So this is reabsorption, taking stuff that is in the tubule and bringing it back into the body. And like I mentioned, about 65% of the filtrate is reabsorbed here, which means by the time we get to the entrance or to the end of this process, like when we get here, we're down to about 35 mils per minute. I mean, again, let me try to write a little neater. And because we're reabsorbing we're reabsorbing both solute and water, we're still about 300 milliosmolar. So that is the PCT. There are a lot of details about how it does what it does that you don't have to know in detail. Some of what it is doing, you already know from transepithelial transport. Remember how we talked about transepithelial transport with absorbing glucose from these intestines? It's the same like here. When you're pulling the glucose back from the tubule into the bloodstream, it's the same basic idea, right? It's going to be carriers and secondary active transport and symports and things like that. And in fact, when we talk about diabetes a little later, like why, there's a limit to how fast you can reabsorb sugar from, because we talked, nutrients like glucose ends up in the filtrate. And obviously, in general, you want to pull all the glucose back into the bloodstream. You don't want to pee out glucose. Glucose is like gold in terms of like nutrient energy. But that process of reabsorbing the glucose involves carriers. If you remember, the glucose carrier was an important part of transepithelial transport. And what do we know about carriers? How are carriers different just from like pores and stuff?
They use ATP.
There's a limit to how much.
No.
Yes, Stephen's got it. Say that again, Stephen.
Well, there's a limit to how much they can go across the membrane because
they're rate limited. We talked about facilitated diffusion, where there's a limit to how fast things can move across if you're using carrier, which means there is I think that's done. There's a limit to how fast you can pull the glucose back into the bloodstream from the PCT. So like in diabetes, where you have way too much sugar in your blood, which means you have really high levels of sugar in the filtrate, means you get past the PCT before you've reabsorbed all of the glucose, which means some of the glucose ends up making it into your urine. So that's like part of one of the main symptoms of diabetes mellitus is there is sugar, there's glucose in your urine. That glucose in your urine is because there's a limit to how fast you can reabsorb the glucose here because of the processes that we got to meet in the very beginning of the class. So you can kind of see how it's all kind of connecting. Okie dokie. The next part here is the loop of Henley. And there's a descending limb and there's an ascending limb. The properties of these two parts of the loop of Henley are super different. And I'm going to describe first their basic properties, but then I'm going to talk about how they work together to create this really important gradient as you go down into the kidneys. So let me just tell you about the properties. Descending limb. Permeable to water. So water can cross in and out. Not permeable to salt, or to solutes, I should say. So descending limb, permeable to water, but not permeable to solute. And again, this is all going to make sense in a few moments. The ascending limb is very different, impermeable to water. So impermeable, not permeable to water. Actively pumps sodium out of the tube. So it's actively pumping sodium out of the tube. That's driven by ATP. And for this also to make sense, we have to kind of bring up this idea. Like a pump has a certain amount of, whoops, back. Think about, actually, let's change, let's say there's a fountain. Let's say you've got like a fish fountain and there's a water in here and there's some pump that takes the water and goes up, and then the water goes, and then the water falls back down. Then the pump pushes the water back up and it goes against gravity, but then gravity pulls it back down. So this should feel kind of intuitive. That's like if you had like some cool in your backyard, you had like a pump pushing a water up through a statue of a fish, and it looks like the fish is spitting up into the sky. You know, how high the fountain goes depends on how powerful the pump is, right? Because you've always got gravity pushing back. So the stronger the pump, the higher the water is going to go before it starts falling back. When I'm in my loop of Henley, pumping sodium out of the ascending limb of the loop of Henley, you know, I'm using ATP to drive this. I'm pumping out, this is active pumping using ATP. The amount of strength that this pump has, because remember, the more sodium I pump out here, I'm going to have an osmotic gradient that wants to make it want to move back in, right? As soon as I have more sodium out here than in here, there's a, not osmotic, diffusion gradient. There's a, as soon as I start pumping sodium out, sodium wants to come back in. So this pump is able to maintain a difference of up to 200 milliosmolar between the inside and the outside. Right, so if this pump is going full bore, it can be 200 milliosmol or higher outside than inside, but at that point, the drive to push, come back in overwhelms the strength of the pump to push it out. So if it is 300 inside, it can pump it out. You know, it can be 500 outside and 300 inside, but I can't make it any more. If it's 500 outside, I can't make it even lower inside because there's too much of a force trying to come back in. So the highest difference you can have between the inside and the inside can be 200 milliosmolar lower than the outside. So what I'm going to show you now is pretty cool. So you've got to think about this loop of Henley. Again, the descending limb permeable to water, not permeable to solute. The ascending limb, not permeable to water and actively pumping sodium. And what I'm going to do now, I'm going to share some, these are actually PowerPoint images from the textbook I used to use. The woman who wrote the Sherwood book, Laurel A. Sherwood, this is more of her bailiwick. So she actually has some better images than the Silverthorne. So I'll put this PowerPoint up on the canvas as well. But what you need to think about here, again, I need to get my little pointer. Let's see. Again, we're in the kidneys. Here's the kidney. And again, the kidneys have all of these nephrons in here. That's supposed to be a PCT. This is supposed to be the loop of Henley, the descending limb, the ascending limb of the loop of Henley. So there are different populations of nephrons. The ones we're going to worry right now, they're called juxtamedullary nephrons. These are the ones that send their loop of Henley way down deep into what we call the renal medulla, the deep part of the kidney here. So there's this cortical part, the outside part of the kidney, but then these loops of Henley are going down deep into kind of more of the core of the kidney, what we call the medulla. So, and again, this part permeable to water, not solutes, this part pumping sodium out. And what's going to happen is pretty trippy. Well, hold on, I went too far. There it is. Okay. So this is going to be what's going on. This here is the initial scene. This is, imagine, so this is not what it looks like in your kidney, but imagine everything in the kidney is at 300 milliosmolar. It's 300 milliosmolar inside and outside of the loop. And then we think about the ascending limb is pumping sodium out. So it can pump sodium out till it's 200 higher outside than inside. But now as it becomes more or higher osmolarity outside on the descending limb, we're going to have osmosis. The water inside the tube is going to leave because of osmosis. So because the two sides are different, one side is pumping salt out into the outside. The other side is going to lose water because of osmosis. And then as that happens, you know, there's flow. And now we can kind of, oh, she doesn't. So this keeps going and going. Oh, dagnabbit. If you keep going and going, okay, I thought this had it. I need to go into another. Hold on, sorry about this. La, la, la. Here it is. All right, so it's kind of where we were. We move this forward in time. You keep going and going. It's gonna keep happening until it kind of reaches an equilibrium. We're down at the bottom of the loop of Henley. It's about 1,200 milliosmolar. Near the top, it's going to still be 300, but because of this pumping and osmosis and the flow through the loop, by the time this whole thing is done, you've got this osmotic gradient inside the, hold on, let me see, slideshow from current slide. This is the cortex. This is where kind of the glomerulus is. And then we have that whole loop of Henley going down. That loop of Henley is creating this osmotic gradient, where as you get deeper and deeper into the kidney, it becomes more and more salty, so to speak, higher and higher. 4 times the osmolarity down in the deep part of the kidney compared to the cortex, to this outer part. So that's going to be critical when we look at how the kidney is going to pull the water back into the body. This really high osmolarity down here in the deep parts of the kidney are going to be used to pull water back into the body by osmosis. So that's important. Boo, 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 boo. So again, this is the reality more of what the nephron is looking like. We've got the glomerulus. Here's that PCT where we have all that reabsorption happening, and you can see the peritubular capillaries all around it, where the water and nutrients and stuff are getting pulled back into the body. Here we have the loop of Henley coming down, which is helping create this gradient. Then we're going to have the DCT, and then this collecting duct, which is going to be important too. The collecting duct, which a lot of nephron, you can have more than one nephron go into one collecting duct, but the important thing about the collecting duct is it's going down through that high osmolarity area. To get out of the kidney, it has to go through the medulla. So as we go down through here, we're going through that super salty area. Again, down here I said is more like 1,200 milliosmolar, 4 times the osmolarity of up here. So as we travel down through here, it's going to be super high osmolarity outside, which gives us the opportunity to pull water back into the body. So keep that in mind as we finish up our discussion right now of the nephron and the collecting duct. Okay. Glomerulus, Bowman's capsule, PCT, descending, ascending limb of the loop of Henley. So like I said, PCT, again, we are reabsorb about 60% of filtrate. So by the time we get here, again, up here we started at 100 mils per minute. By the time we're here, we're about 35 mils per minute. 300 milliosmolar. So now we've added in this other factor now, though, that, just in the kidney, it's about 300 milliosmolar outside. When you get down here, it's about 1200 milliosmolar because of the property of that loop of Henley. So now, here in this descending limb of the loop of Henley, which we said is permeable to water. If it's permeable to water and the filtrate that's coming down is 300 milliosmolar and it's 1200 milliosmolar outside, what's going to happen?
Water will go out.
Water's going to totally go out. So we have osmosis, we're losing water. By the time we get to the bottom of the loop of Henley, we've lost like another 15, 20% of the original volume. So by the time we're down here, we're down to maybe 15, or it's actually more like, I think it's like 20, like about 20 mils per minute. Because we have just lost a whole bunch more of the water due to osmosis. Because water is leaving, but no salt, it was not permeable to solute. We have about 1200 milliosmolar. It basically equilibrates. Water leaves until it's the same inside and outside. But then when we go up the ascending limb, we said the ascending limb is pumping out sodium. So by the time we get to the top here, what is the inside going to be? If I can be 200 less than the outside with this pump,
Be 1,000.
no, remember what?
Or 100, it was.
Right, exactly. We're down to like, so it's actually much more dilute than normal body fluids. Down here, it can get down to 1,000, but as you go up, we have this gradient which goes from 300 to 1200 as we go from what we call, this is the cortex, the kind of outer part, the medulla, the inner part. So by the time we get to the top here, and because we're not losing water, this is still maybe about 20 mils per minute. So we have much dilute, but still quite a bit of, 20 mils per minute is still a lot of fluid. This is going to finally go into this collecting duct, which we need to talk about as the last part of this. So this is going to leave the kidney. So this is going to be to the ureter here. Right. Again, if you've been in anatomy, the collecting ducts all feed into those little renal papillae, into the minor calyces, into the greater calyces, into the renal pelvis, into the ureter. So at the end of the collecting duct, it is urine. It's what leaves your body. But the collecting duct is the last opportunity to adjust things. Oh, and I forgot, this is the DCT here, the distal convoluted tubule. The distal convoluted tubule, it has more secretion as well as some absorption as well. But it's just more places for things to either get into the tubule from the blood or leave the blood into the tubule. But the DCT does not do a lot of dramatic reabsorption. So we have about 100 mils per, about 20 mils per minute entering in the DCT. There's about 20 mils per minute entering into the collecting duct here, which means if you did not reabsorb any more of the water, you would have a large volume of pee. So we can pull more water back into the body here. Typically, you end up reabsorbing almost like 99% of the original volume of the filtrate. To pull water back into the body, we are going to have these little aquaporins. So they move H2O across the membrane. They're called aquaporins. If the aquaporins are open, you're going to be pulling a lot of water back into the body because it's 1200 milliosmolar outside, right? And the stuff coming in is 100 milliosmolar as it's kind of entering in. So if it's 100 milliosmolar inside and 1200 milliosmolar outside, the water is going to go back into the body. The aquaporins are under the control of the hormone you've already got to meet. What hormone is in control of aquaporins?
ADH.
Antidiuretic.
Yep, this is regulated by ADH. So ADH, which is a hormone that's coming from the pituitary gland, we'll talk about it in more detail. But if you have lots of ADH, you open up more of the aquaporins, you pull more of the urine or the water back in the body. That means you don't pee as much, right? Instead of having the water leave, the water is getting pulled back into your body. Alcohol inhibits the release of ADH. If I inhibited the release of ADH, what would that do?
You would lose more water.
Pee more.
If I don't have these aquaporins open, that means I'm just going to have much larger volumes of very dilute urine coming out because I'm not going to be pulling the water back into the body. Right? If I have 100 milliosmolar stuff coming through, but the walls are all sealed, then it just makes it all the way through. If I do have ADH and the aquaporins are open, then osmosis, the water gets sucked back into the body. So that's one of the big things happening in the collecting duct. The one other thing happening in the collecting duct is a hormone which you've also met when we talked about the renin-angiotensin, aldosterone, can turn on additional sodium reclamation here. So this is getting really messy. So reclaim sodium if aldosterone present. So there's two hormones. This is getting so messy. So collecting duct. There's two major hormones at work here. ADH and aldosterone. Again, you think about, here's the kidney. Like I said, it's like 300 milliosmolar up here, but like 1200 milliosmolar when you get down deep. There's that gradient. And the collecting ducts are basically draining, going down, and ultimately going to leave the body. So here's a collecting duct. Which is, getting, here's my nephrons are feeding into this. So antidiuretic hormone is going to open up water channels. Water channels mean H2O is going to come back into the body because, again, the filtrate entering here is only like 100 milliosmolar and it's 1200 milliosmolar outside. So the water gets sucked back into your body. Aldosterone is going to turn on sodium pumps that reclaim sodium back into the body. These can be independent. You can turn one or the other on or off, either open or close the aquaporins. Turn on or off the sodium pumps. But if you have both working together, that's going to be the most, if you're really trying to hold water in your body, you do both of these, which we saw in the renin-angiotensin mechanism, right? We turn down aldosterone, which pulls even more sodium back into the body, and we turn on ADH, which opens the aquaporins. So that's even going to be even more of a gradient to reclaim water. If we're pumping sodium as well as got the intrinsic huge gradient, that's going to be the maximum ability to keep water in the body. So these can be independent, sodium balance versus water balance, but if you're really trying to keep water in the body, you can turn them both on. So, other questions about that? Okay. So again, nephron. Kind of the PCT, which is reabsorbing. Loop of Henley, which creates and maintains that osmotic gradient, which is essential for the kidney to function, as well as more reabsorption. The DCT, another thing the DCT does, which is going to create what's called the Juxtaglomerular Apparatus, so there's this little junction. I'm not going to go into detail because of time right now, but basically, in a nutshell, there are special cells in the arterioles, and there are special cells in the DCT that work together to become what's called the Juxtaglomerular Apparatus, which you should know the name of this thing. So juxta means near, glomerular meaning, so near the glomerulus apparatus. So these are specialized cells within the arteriole and the tubule. And they monitor both blood pressure, right? You know, just stretch of the arteriole is going to give you a measure of blood pressure, right? We've talked about how stretch receptors can detect blood pressure. You know, and also they also monitor filtrate composition. Right, the DCT can monitor like the osmolarity, like how much stuff is dissolved, what's going on inside the tubule. So both of these are part of this process to make sure the glomerular filtration rate stays intact. If the blood pressure is dropping, or if the filtrate composition looks off, again, we're not going to go into the detail. There's a variety of things this thing can do, but what's one of the main things that is going to be released here if your blood pressure is dropping to keep the glomerular filtration rate up?
Renin.
Exactly. So that's why I wanted to make sure that I brought this in. This is releases renin. You know, in particular, what would cause it to release renin?
Detection of low blood pressure.
Exactly. If it detects a drop in blood pressure, then we're going to release renin. Just as a review for your exam on Tuesday, what happens next once it releases renin?
So that convert angiotensinogen into angiotensin 1.
Exactly. So first step, angiotensinogen becomes angiotensin 1. What happens next?
It gets converted into angiotensin 2.
Yeah, angiotensin 1 becomes angiotensin 2 through the action of angiotensin converting enzyme, ACE. Like I said, one of the major drugs for high blood pressure are ACE inhibitors, things that are going to stop this process at this point. But assuming you're not on an ACE inhibitor, what happens next to bring your blood pressure back up?
Vasoconstriction.
So one, angiotensin 2 is a potent vasoconstrictor. Vasoconstriction increases resistance, brings your blood pressure up. And that's one piece. What else?
ADH and aldosterone are released.
So ADH is released from the pituitary gland, which we've just been talking about. What are the different things ADH does to keep your blood pressure up?
Reabsorbs water.
So one is it's keeping the water, keeping your blood volume up. We just saw it's about keeping water in your body, and we said keeping blood volume up is an important way of keeping your blood pressure up. What else does ADH do?
And it's a potent vasoconstrictor.
It's a vasoconstrictor as well, which is going to do upping blood pressure by increasing resistance. We also talked about how it talked to the hypothalamus and increased thirst. So you brought more water in your body to increase your blood volume. And then there's aldosterone. What is aldosterone doing to help with blood pressure?
Conserves sodium.
What's that?
It conserves sodium.
So it's the one that tries to pull sodium back in. And by pulling more sodium in, that's going to increase the amount of water retention as well to keep your blood volume up. Right? So all of those things, that's important. I promise you there will be questions on your exam where you need to understand the renin-angiotensin mechanism, because it's a critical part of your blood pressure control. So make sure that all makes sense, everything we just talked about. And again, it's being initiated by this juxtaglomerular apparatus here. So any questions about that? All right, let me take a look to see if there's anything else that's critical that we didn't talk about. Let me go back, share screen. Again, just kind of to review everything. The kidneys are complicated. There's a lot going on. You should know it at the level that we've been talking about it. When you read in your book, it's going to talk even more detail about things. Don't get caught up in the nitty-gritty details. Think about the bigger picture that we've addressed in the class. Again, you should definitely know the main idea of kidneys getting a quarter of your cardiac output here, processing, doing all those things. Whatever finally leaves goes out the ureter. The idea of having 1,000,000 nephrons all working in parallel, doing filtration, tubular reabsorption, tubular secretion. The idea that there is this gradient, it's normal 300 milliosmolar in the cortex, but you get down to like 1200 milliosmolar down in the medulla due to the activity of those deep loops of Henley. Oh, here, internal sphincter. Again, the one that is smooth muscle. This one is just going to relax based on stretch of your walls of your bladder. It's going to be a spinal reflex integrated in the spinal cord. When that one relaxes, you get more pressure down on the external sphincter. That's when you have the urge to urinate. Again, external sphincter, which is actually kind of part of your pelvic floor muscles, that's skeletal muscle. So then you can choose, is it time to pee or not? You can relax it, and if you do, you pee. And again, when we get to the male, we're going to see there's a lot more going on. This little space between the internal and external urethral sphincters are where we're going to mix all the different components of the semen in the, we'll call the emission phase of ejaculation before the expulsion phase, where you actually have the white goo come out. Again, this idea, you have the initial capillary bed, which is the glomerulus, where you're creating the filtrate, but then that feeds into a second capillary bed, the peritubular capillaries, where we do the reabsorption and secretion. Because the filtrate, you're making, again, 180 liters a day, including all of your good nutrients and stuff. So you're going to be reclaiming almost all the water, all the good stuff before you finally get to the very end. Again, collecting duct's the final step. And then at the end of the collecting duct, you're heading out the body, and that's going to be your actual pee. Oh, this is a cool image of a glomerulus. This is just kind of showing this the more schematic. And again, like I said, filtration, reabsorption, secretion, and then ultimately leaving the body. This is kind of cool. This is showing, like I said, the podocytes, the little cells that glom onto the capillary, make these little slits to make that filtration membrane. Again, this is a cool photomicrograph showing those little slips there. Again, this is talking about net filtration pressure. 55 millimeters of mercury is the hydrostatic pressure of your blood coming in, but you've got about 30 millimeters of mercury osmotic pressure pushing back against there. About 15 millimeters of mercury of the just the capsular hydrostatic, basically the back pressure, which means net filtration pressure is about 10 overall, 10 millimeters of mercury. And that's what's driving filtration. Again, if your overall blood pressure drops too low, so you don't have this original one, then your filtration stops and you're going to be in renal failure. Oh, this is showing the juxtaglomerular apparatus, kind of specialized cells in the tubule, specialized cells in the arteriole that are detecting your blood pressure, detecting the content of the filtrate, and making a decision on whether to release renin or not into your body, and do a whole big cascade of the renin-angiotensin mechanism. You know, here we're talking about all this transepithelial transport. Don't get too worried about this. Yeah, so this is where I'm saying don't get too concerned about details. All right, this is just showing the arterioles coming in into all the little glomeruli. It's just pretty. All right. Let's see. So are there any questions about any of that?
But even like a more generalized question, like things that affect blood pressure, like end diastolic volume would be an appropriate answer, or like you're just not even going to write the question to be like that tricky. I'm just trying to figure it out to kind of help with my studying techniques.
No, I mean, I think the fact that you're asking that question means that you are understanding all these relationships well.
Mm-hmm.
Because ultimately, right, I mean, part of the reason, here I can go, you know, the beta blockers. You know, why do people take beta blockers for high blood pressure? You know, one of the things that beta blockers do is reduce contractility of the heart muscle. Reduce cardiac muscle contractility, contractile strength. And that is going to mean that you are going to reduce, increase end systolic volume because it's not squeezing as hard. So we're going to have more blood left still after we're done with end systole. And stroke volume was end diastolic volume minus end systolic volume. So if this is going up, stroke volume is going down just because of the math. And then we know that stroke volume times heart rate is cardiac output. So if stroke volume is going down, cardiac output's going down. And then we know blood pressure is cardiac output times resistance. So if cardiac output's going down, keeping blood pressure down. So actually, to understand one of the reasons beta blockers are useful, you actually do have to think exactly like you're saying.
Okay.
Like if I have a question about beta blockers, you'd have to understand both they're affecting stroke volume, which affects blood pressure.
Mm-hmm.
They also affect heart rate though too, right?
Yeah, so heart rate, which is also going to be bringing, so both the stroke volume and heart rate come down or stay down, which keeps the cardiac output down, which keeps the blood pressure down. Yeah, no, exactly. So, yeah, no, so, yeah.
With the loop of Henley, like you were saying that as you get deeper into the kidney, the osmolarity goes through the roof.
Yeah.
I'm not really understanding why, because in that descending limb, water is coming out, and then on the ascending limb, it's pumping solutes. It's pumping the sodium back in. So like, wouldn't the two balance each other out? I don't know why I don't know if I'm phrasing it right, but
Because there is a flow. Here, I'll show the thing in the Laurel Sherwood. Let me find it. Here it is. Yeah, this is it. Okay, I'm going to share this with you. It has to do with the fact that things aren't static. The fluid is moving forward through the loop of Henley. So here, let me see, I'll do the slideshow from current slide. And let me get a pointer. Let's change the color. All right. So again, this initial scene, this is artificial. This isn't real. But let's just assume we have something that's completely homogeneous. All right. In which case it's 300 milliosmolar in all the extratubular, and it's 300 milliosmolar in the filtrate that's moving through the tube. But then it's also important to remember that the fluid is moving down here and up here. So moment to moment, it's continuing to flow. So then she says, all right, let's go over here. As we start, we have to go over here. In the first moment here, number one, we have this is the ascending limb pumping out. So it can pump to 200 milliosmolar difference. So it was, remember it was 300 in here. It was 300 everywhere when we started. Now it's 200 in here. And it's 400 out here because we just pushed all that sodium out. And as soon as it's 400 out here, water is going to leave the descending limb because of osmosis, because this is permeable water. So now things flow. Fresh 300 mils comes down from the top. This 400 mils is now starting to go up the other side. Once it's going up the other side, we now have that 400 here is now 300 in here and 500 out here. And this is now equilibrating the 500 in the descending limb. So now it's 500 here. And now, keeps flowing. Now we have 500 starting down here. And now when it's 500 down there, now it's equilibrates as we pump out the sodium.
Oh, okay.
And now this is 600, and this becomes 600 because this is osmosis. And now that 600 flows up into there. And when that 600 flows up into there, now all of a sudden we have, ultimately you end up getting where it finally stabilizes is when 300 is coming in from the top constantly, 1200 at the bottom. So this is kind of just where it equilibrates.
Okay. I think I get. Are we recording this? This is a good explanation.
Actually, I am recording it. Yeah.
No. Yeah. It makes more sense now. It's thinking about the flow.
Yeah, you have to. And on your exam, I'm not going to hold you accountable to the details of this. You should know that the properties of the loop of Henley are responsible for creating and maintaining that gradient, but don't worry too much about making sure you can reproduce this explanation. This
creates that gradient.
It creates and maintains it. And I think it's totally cool how it does it. Again, in the Sherwood book, she spends more time going into the details. I don't think Silverthorne goes into the details as much. But I think it's really kind of cool. But yeah, that's what's happening there.
Okay. Yeah, I think I get it now. All right.
And I just shared a video that was in my anatomy class from last semester that Tina had shared with the class explaining that flow.
Oh, thank you.
Yeah, no problem.
Cool. Let me, so you put it in the chat.
Yeah.
I wonder if let me try to save that so then I can just post
Want
it
to
to
know
everybody.
why running on the treadmill 7 days a week doesn't work for you when you're trying to lose weight? Because it
Right, these ads. But yeah, so Emily, I'll put that up on the website. So
Okay.
on the Canvas module, so people can see that. But don't get too caught up in that. I don't want you to spend a lot of time learning the details of that as opposed to learning just the fundamentals.
Okay. All right, Dr. Again, thank you.
Sure. All right, have a good weekend.
Yep, you too.